Thank you very much. So this is a sort of a propaganda talk for the field of toroidal electrodynamics, and I'm here talking on behalf of three people who have been involved in this work for recent years. But in fact, it's one of the beloved stories in our group for quite a few years now. So this is a short, maybe incomplete list of various discoveries which have been possible in electrodynamics and optics as a result of introduction of the field of metamaterials. And of course, perhaps the most well-known is negative index of refraction, optical magnetisms, and many other things listed here. Among them is a discovery of toroidal moments, anapoles, and flying donuts, which have become possible as a result of the field of metamaterials. So just to introduce the whole idea, you can see here an artistic representation of a transversal electromagnetic wave. So this is another type of propagating electromagnetic solution, which is exact solution of the Maxwell equations and has a form of a flying donut. And so I will end up with talking about recent development in the field of flying donuts, which are non-separable solutions of the Maxwell equations, where you cannot separate coordinate and time, while in transversal electromagnetic wave you normally can do that. And I will also talk about anapoles. And if you don't and then never heard about anapoles, this is perhaps could be an interesting talk for you. So toroidal structures are represented at all levels of nature. For instance, this is the artistic impression of a nucleus, which some of them have persistent current, and this currents called create a toroidal response. So this is a form of benzene which has a toroidal element. This is a fullerene, which also you can see looks like toroid, and then DNA and protein structures. So the field of toroidal dynamics started actually about 40 years ago from a group of Russian theorists in the Nuclear Science Institute in Moscow. And they were starting this field by introducing essentially a fractal type complications of ring current. So this is a conventional ring current. And you can then see that the next stage would be to replace all linear currents with ring currents, with a chain of ring currents. And you can make it more and more complex using this principle. As a result, you create a family of what they're called super-toroidal currents. So the first toroidal moment is defined as essentially equivalent to the magnetic moment of a current loop. And then toroidal moments of higher order of currents are represented by this formula. So interestingly enough, that if you look on a current loop or super-toroidal current loop from a distance, at distances which are much longer than the diameter of this structure, the current can be represented as a several applications of the curl operator on the delta function, which simplifies a lot of mathematical computation. So there are odd order toroidal currents. Say a loop is a zero order, and then complications of them. And there are even number toroidal currents. So the first one, actually, the far field radiate as magnetic dipoles, and the odd ones radiate as electric dipoles. So interestingly, if you would like to find the energy of interaction of magnetic or electric type toroidal currents with external fields, this energy of interaction is proportional to the derivative of the magnetic and correspondingly electric field, which is order of derivative is equal to the order of toroidal moments, which is a very unusual situation, of course. And this leads to the number of interesting paradoxes, which are still being discussed in the community. For instance, if you have a zero-order toroidal current, which has oscillating current in it, right? So this will be a magnetic dipole emitting electromagnetic wave, and you can show by direct integration that this electromagnetic field will create a torque on the toroidal order of the toroidal current of the first order, in which the current is DC. However, it is well known from actually 1971 that a perfect toroidal transformer does not have any field outside of it, and therefore back action of the DC current in toroidal transformer will not affect the AC current in the ring. So there's an apparent violation of action-reaction inequality, which has been addressed in a very high detail by Afanasyev in his paper in 2001, and he has shown the energy of interaction of two toroidal currents of different order is actually in a way violate the second Newtonian law. And he, as a result of that, he revised the applicability of the Lorentz lemma to super-toroidal currents. I'm not going to produce any comments on critique on that. I'm simply saying that this is a lot of interest to the subject here and a lot of controversy. Right. In fact, the field of toroidal electrodynamics was started by Yakov Zheldovich, a famous Russian theorist, in 1957, when he was talking about persistent currents in nucleus. And this persistent currents creates toroidal moment, which has very interesting fundamental symmetries, and in particular is partially responsible for parity violation of light interaction with atoms. You remember perhaps that there was a very intense search for parity violation manifestations in optical spectroscopy, where a gas of certain atoms, cesium, for instance, if light goes through a highly forbidden resonance in such an atom, there will be polarization rotation, which is relevant to the weak interactions between the electrons and the nucleus, and these weak interactions break parity, and therefore rotation is possible. This eventually got the Nobel Prize. Actually, about 40% of this contribution is relevant to the presence of persistent currents in nuclei related to the toroidal dipole. So a toroidal dipole, in terms of Zheldovich and persistent currents, is a static feature. So obviously, for electrodynamics, a very considerable interest was in discovery oscillating dynamic toroidal dipoles. So our group in 2009 published the first indirect observation of toroidal dipole in the Metamaterial, but explicit demonstration of toroidal dipole came in 2010, which is then resulted in the science paper and a very considerable follow-up. So essentially, we created a material structure in which individual metamolecule was a combination of 4 split rings. As a result of excitation of a plane wave propagating in this direction, the magnetic moments are created in these rings, creating a toroidal response, toroidal dipole in the system. And this toroidal dipole is seen as a peak in transmission and reflectivity of the system. And analysis shows that in this particular configuration, toroidal mode is the main contributor to this electromagnetic response. So then this created a considerable follow-up. I need to say that the number of papers on toroidal response in materials is now in thousands, and but original papers were in terahertz part of the spectrum and microwave part of the spectrum, and then in dielectric and plasmonic metamaterials, and even excitation of toroidal moments in clusters of particles using near field of free electron beams. So a considerable effort was put into understanding of origin and the genesis of toroidal response, and it's now well accepted that toroidal moments is small but significant contribution to the electric multipoles, and exist in the multiple expansion alongside with electric dipoles. They are sometimes difficult to distinguish with electric dipoles, but I will come to this later. And this was initially recognized by Dubovik and Tugushев, these people who looked into the static moments as well. So in 2015, an analysis has shown that by Merstchenko and others, that this toroidal dipoles are also contributed to the first mean-theory coefficient on the scattering field. So, however, the important rule is that if one wants to have a sizable toroidal response, one has to have your structure, which is topologically has elements of toroidal symmetry, and also toroidal response, which is essentially an local response, increases with the size of the molecule. So the closer your molecule is to lambda size, wavelength size, the stronger would be toroidal response. So there's also the whole family of toroidal multipoles alongside with electric and magnetic dipoles. You have dipoles, you have toroidal quadrupoles, octupoles, and you name it. And all of them, which is most importantly, contribute or can contribute, depending on the symmetry, to the optical response of the matter. And in order to illustrate that, I show you a couple of examples. So the first example is, you perhaps all are familiar with optical activity, polarization, plane rotation through scattering on molecules. And this resulted from consecutive events of, for instance, dipole absorption and the magnetic dipole emission. As a result of that, you see polarization rotation, which can also become possible as a result of dipole absorption and quadrupole emission. So here, what may happen is that one of the elements of this scattering diagram will be replaced by toroidal response. For instance, toroidal absorption plus quadrupole emission. This has been demonstrated in a number of experiments. This is our experiment when we show that one of the lines in a chiral metamaterial actually directly related to the combination of electric quadrupole and magnetic toroidal dipole. An interesting idea, I believe, was to look at the role of toroidal dipoles into electromagnetic properties of matter in standing waves. And the reason is very simple. So if you have a standing wave and your very thin sample is positioning in the node of the standing wave, then electric field there is zero, and you cannot see electric dipole contributions. If you move it to an antinode, you will see the maximum of electric field, and you will see considerable contribution from electric dipole and toroidal dipole, but magnetic dipole will be suppressed. And this has been demonstrated in a number of experiments with metamaterials, and in particular, you can see that the radiation power spectra of metamaterials, depending on whether it sits on antinode or node of the electric field, are different, and putting the antinode emphasizes the toroidal response. So a very recent result goes beyond the classical description of toroidal dynamics. So if you can think of a magnetic dipole as a current, you of course within relativistic quantum mechanics, you can also think about magnetic dipole as a spin. Correspondingly, toroidal moment may not only be presented by colloidal current or on a torus, it can be presented by appropriate arrangements of spins. And this has fundamental consequences. The fundamental consequences is that even in a very, very traditional, very symmetric, very well understood quantum mechanical system of a single electron atom like hydrogen, you can identify terms in the fine structure of the hydrogen atom, which would allow toroidal transitions, and on which electric dipole transitions are actually forbidden by selection rules. So this is a very new work. It would require the entire lecture for me to show, but this is now on archive. You can see it here. The discovery of dynamic anapole was then a next important stage in developing toroidal electrodynamics. What is anapole, dynamic anapole? So if you, as I said, the far-field emission of electric dipole and toroidal dipole are exactly the same. And therefore, if you if you superimpose electric dipole and toroidal dipole, this is electric and toroidal, put them together, then adjust their phases, and then reverse phase of emission of one of them, you will see complete cancellation of the radiating fields. And this creates an anapole, a charge current configuration where charges and currents moves, but no emission happens. And this would be called dynamic anapole. A very interesting feature of such structure is irrespectively to the gauge, the fields outside of the anapole in the far field are zero, but vector potential is not. And this created a considerable body of literature to see if this vector potential field real, can it be used for telecommunications? And I don't want to go into that, but I want to go to show you that anapole structure can be created. So we did it in 2013 by suggesting metamaterial in which a piece of metal, a metamolecule is made by cutting dumbbell openings with a little gap in between them. So then what happens that the electromagnetic wave rises along these directions, create dipole response in the structure, and simultaneously induce currents going around these loops. And these currents together create a provision for magnetic response of the structure in such a way that this all together makes a toroidal response. As a result of that, for the right configuration and right symmetry of the structure, you need to combine a few dumbbells to have a proper anapole metamaterial. You will get for a particular wavelength a situation where anapole is created. As a result of that, this metamaterial structure actually does not interact with the free space wave. So the coupling becomes zero because cancellation of the responses, and you see a standing, self-standing, very sharp peak in transmission and no reflection. So this was an observation of anapole in the microwave, and the first observation of anapole. And I wanted now to show you how actually you can detect the presence of anapole, because they're not visible to electromagnetic radiation. So how would you know that the system supports anapole? It's now a very big literature, but let me give an example of how this could be solved by what we call solvatochromism idea. In this idea, we exploit the fact that, excuse me, that the emission power of toroidal dipole, electric dipole, differently depend on ambient refractive index. So electric emission power proportional to the refractive index, and what toroidal moment is the power 5. So if you had a perfect anapole structure in, say, in vacuum, and then immerse it into liquid with different refractive index, the anapole is then broken, and as a result of that, you can see now absorption and the reflection lines of the combined electric and toroidal dipole. Another idea is more exotic, but still physically very important, is that if you have an anapole created by a combination of electric and toroidal moment, and which does not radiate, but then you, actually, video doesn't work here on Macintosh, never mind. But then accelerate the structure with velocity, which is a relativistic velocity. The structure becomes radiating, right? So it's a result of the fact that toroidal and electric dipole behave differently when accelerated. Sorry, when I said not the velocity important, the acceleration is important. This work on its own rights resulted in a very large body of literature of anapoles, which are essentially charge current configurations which are not coupled to free space and therefore concentrating a lot of energy. And they have been observed in all types of across the whole electromagnetic spectrum, from visible to microwave, and they are now used to generate systems with high nonlinearity because of high concentration of fields. Metamaterials supporting toroidal supporting anapoles have been demonstrated starting from 2018 by our work with Taiwan, and it's now used in various aspects of nonlinear optics, and even anapoles are now considered as valuable qubits in quantum physics. Toroidal excitation I just talked about are localized and sort of seeds on metamaterial or metamolecule level of localization. But from now on, I will be talking about flying toroidal structure that I promised at the beginning. And this is essentially sort of continues as this trend. So I talked initially about static toroidal excitation, then dynamic when toroidal current oscillates on the torus, and then I'm talking about a situation where this structure can fly. And this structure is indeed can fly, and this has been shown for the first time by Helvers and Nauchi in '96, resulting into a structure with essentially a single pass electromagnetic excitation, which propagates in free space with speed of light, and which can be focused and defocused in very much the same way as a Gaussian pulse. So the very different from many other excitations is that it is either diffracting. Therefore, if you make a cross section of this structure here, and there, you will see that different spectral components propagate without mixing. So this is the bluish one, this is the reddish one, this is infrareddish, and they do not mix. And this is called the either diffraction properties. So these solutions actually came as a subset. It was identified theoretically by Helvers and Nauchi. It came as a subset of more general group of solutions which were identified by Richard Minkowski a few years before, which starts from the following seed function. So this seed function would satisfy the wave equation, and then if you convert this seed function through vectorial operation like that, you have vector potential of the electric and magnetic fields, which will satisfy the Maxwell equations. And this has resulted in sort of electrodynamics of flying donuts, which for many, many years was a theoretical subject. The most important part of this consideration is that transverse electromagnetic waves is good to excite toroidal, is good to excite conventional electric dipoles, while flying donut, as we call it now, is very good to excite toroidal excitations in matter. and also dynamically in transient regime couples to Anapoles. And this attracts considerable attention to that. But it took quite a few years to realize how actually one can generate such flying donuts. So our concept, published quite a few years ago now, was to start with conventional electromagnetic pulse, then convert it into a radially polarized pulse, and then use a metamaterial, singular metamaterial surface, which would affect the retardation and spectral composition of the radially polarized pulse, creating a flying donut. It was quite easy to demonstrate this possibility. Another thing, it was quite difficult to actually complete the research, and this is an example of singular metamaterial arrays and gradient type metasurface like an antenna. We have now completed this research and have been able to show that appropriate metasurface and radio polarizer can create a flying donut. And we actually also created a transient technique for vectorial mapping of the fields in flying donuts. And it took for a few years. And I need to say that this has now resulted in a paper observation of toroidal line pulses, which is now in press on Nature Photonics. And it took maybe more than 4 years for our work finally to show this convincingly that this, what we generate, is really a Hilbert-Tsiolkovsky solution. So now going from toroidal to super-toroidal pulses. Remember, this Afanasyev work I was quoted about 40 years ago was talking about a fractal extension of toroidal currents to super-toroidal currents. In a similar way, we can talk about going from simple Hilbert type solutions presented here to a more complex one. So you remember I was talking about the seed function, which can generate electric and magnetic field, but as a scalar function initially we satisfy the wave equation. So Hilbert and Nauchi studied this case and got this flying donuts for alpha equal to 1 and Q3, which is the parameters of this function equal to infinity. If you now do exactly the same, but make alpha more than 1, you cannot make alpha less than 1 because the energy will become infinite in the pulse. And if you would like to stay in a situation where the pulse is not topological, so it has finite energy, you have to have alpha more than 1. You create increasingly complex structures. So this shows a cross-section of a donut. So donut flies from bottom to up. And you see that for very simple structure of alpha to 1 to alpha to 15, the structure becomes more and more complex. These are either surfaces for electric field in the structure. And it looks like a Matryoshka construction. So I think it's even more interesting is that if you actually make instantaneous cross sections through this flying donuts go in this direction, you make a cross section of this, and in particular, I will look at cross section of super-toroidal pulse. You have several cross sections. If you watch a magnetic field, you will see that they create skyrmionic type structures, and you know skyrmionic type structures is a Hedgecock-like topological constructions of magnetic field, which may be characterized by so-called Skyrmion number, and the Skyrmion numbers can be calculated for all structures absorbed in flying donuts. And I give you simply examples here for Hilbert solutions and more complex Skyrmionic structures for super-toroidal pulse. Of course, proving and demonstrating this experimentally could be a considerable problem because you need to do full transient vectorial analysis of the pulse, which is possible, but extremely labor-intensive, high-quality, ultra-fast work. But we're hoping it will be done very soon. But predictions of flying skyrmionic fields has been a very considerable stimulus, in my view, to the community. And finally, I would like to show you that our very recent work, where we have shown that if you in this seed function explore a situation where alpha is equal to 1 and Q3 is equal to 1, you will have something like Hilbert solution, which can be focused and defocused, but focusing actually stops, and this is becoming non-diffracting toroidal pulse, which you see. So this is propagation of non-diffracting pulse along that direction for Q equal to 1. And this is a typical situation for Q not equal to 1. So it's focusing and defocusing and stop focusing and propagates as a non-diffracting toroidal pulse. And you can see that this pulse has broad spectrum. It is a short, single short pulse. And nevertheless, you can construct electromagnetics in a way that this flies as a bullet. Finally, I would like to show you some conclusions. So in 2010, we observed toroidal dipole response, and then Anapoles, and then the flying donuts. So which you see, if you are interested in solid state physics, in particular in plasmonics, you may be thinking of analogy, which is localized plasmon and traveling plasmon. Here, localized toroidal excitation and traveling toroidal excitation. We are now entering the field of super-toroidal electromagnetics, which is still very much theoretical field. And we think that there will be a field of activity which would revise spectroscopy even of such systems like atoms. In this case, this is about toroidal transitions in atoms, which are possible to distinguish from other transitions. And this requires very precise instrumentation within the time structure of atoms. So this area is growing very rapidly in all directions, and now attracting attention of many funding bodies, in particular of DARPA. Thank you very much. That's all.